first thing in this video is I want to talk about what's happening as we traverse through the circuit. So if we look at what happens to the electric potential, again, analogous to energy, as we cross over the battery, so if we're moving through a circuit and current goes through that battery, and then how it goes through that resistor. So over here I have a graph where the vertical axis is the voltage and the horizontal is actually, if I took this circuit with the wires and kind of disconnected it there and stretched it out straight, what's going to happen to the voltage as we move through that wire. Okay. So if we pick point A and we say that the voltage at point A is 0, so we're going to start at 0 here. And I'm going to write out my equation as I go. It doesn't have to be 0. So at point A there may be some voltage, some potential. So I'm going to start with the value of VA. The potential does not change through any length of that wire until it interacts with something else. Once it gets to the battery, again, the battery acts like a pump. The pump is going to push the charges through the wire. So that's going to basically raise the amount of energy that's in there to the value of the voltage of the battery. Then as the current moves from the battery through the wire, there is not going to be any change until it hits the resistor. What the resistor does is it uses the energy. And what's unique about the circuits are all of the energy will always be used. All of the potential supplied by the battery will end up being used by the time you make a complete loop through the circuit. So as I continue with my equation here, which I actually forgot to add the amount of voltage from the battery, when we get to the resistor uses all of it by the time it gets to the bottom. And the value of that voltage can be found using Ohm's law. So the voltage of the resistor that it's using, the potential, is going to be equal to the current times that resistor, right? And it is dropping. So the value of this drop is negative IR. Okay, so that drop is negative IR. This rise is the total voltage. So in my equation I have minus IR. And then by the time I get back down here and I'll get to point A again, we'll be back to what the voltage was at A. So if VA is 0, you just plug in your zeros for both of those and it simplifies it. However, if there is a value there, if you subtract VA from both sides, you can see that those cancel out, so it equals 0. So we just have V minus IR equals 0, and if we just keep going, we get Ohm's law. Okay, this is really where you need to go. We won't look really at these voltages at different locations. Writing this equation the way that we went through that loop is actually called the loop rule, and it says that the sum of all of the potentials through a complete loop in a circuit is going to equal 0. And so it's kind of like summing up the forces and setting them equal to 0. Here we're just summing up the potentials and setting them equal to 0. All right, so that's a basic circuit, one resistor, one battery. So we're going to look at different combinations of these things. I think the next one we're going to look at is what happens if we just have multiple batteries. What does that look like? Okay, so here is a circuit with two batteries that are facing the same direction. We're going to make this point A and move through that loop, right? All right, so when we move from A to the battery, that battery is going to raise it up, and I'm going to put the values here for each battery. So each battery has a voltage V. So the first one is going to raise it to that voltage. Then as it travels through the wire, there's not going to be any change. There's nothing being used or put in. Then over the second battery, it raises up another value of that voltage. And then as it travels through the wire, nothing is happening until it gets to that resistor. Since there's only one resistor, that resistor will use all of that potential, and it goes back to 0. So what the equation would look like here is, going across, it would raise a value of V right here. So that's going to be V. And then plus another V from that point. And then minus the current times that resistor equals 0. All right, so it still resembles Ohm's law. It'll be the total voltage, which will be 2V, is equal to I times R. So if our batteries were equal to 9 volts, we would just have 18 volts causing the current to flow. And that V is the unit, not the variable V. So now we're going to look at one with resistors in series. All right, here's a series circuit with 3 resistors. Let's go through the circuit loop and look at the graph. Starting at this point right here, we go until we hit the battery. That battery will raise up until it reaches 3 volts. And then the potential stays the same, and then it hits a resistor. Now this resistor cannot use all of the potential. It can only use a small amount. And then as it travels the wire, nothing is going to change, and then it hits another resistor, and that uses a little bit more. Then it goes through the wire, then it hits the last one, and uses the rest. So that each resistor uses a little bit of the potential, but the entire circuit loop is still just equal to 0. So our equation here would be the voltage that it gains minus the current through that first resistor. I'll just label that one as R1, minus the potential across the second resistor, which is IR2, minus IR3, and then that finally ends up back at 0. What we can see is that the total drop over all 3 resistors is going to be 3 volts. So in the prior circuit with only one resistor, that one resistor dropped the total potential. So each of these have their own amounts of drop here, equal to what you put into the equation. So if I add everything up in that equation, move all of the IRs to the other side, so V is equal to IR1 plus IR2 plus IR3, and I is in each of the terms, so I can factor that out. If we were to actually just take the numbers for our resistors and add them all up, R1 plus R2 plus R3, we'd have 4 plus 4 plus 2. So we have I times 10 ohms, all right? What this is saying is this circuit is equal to a circuit that has one 10 ohm resistor. And that's called the equivalent resistance. So if we move through the circuit from this point through, we'd go across the battery, raise up to whatever that voltage was, so that would be our 3 volts. Move through the circuit, hit our 1 resistor, have to use all of the potential, so that 1 resistor will cause a drop of 3 volts, just like all 3 of them did in that circuit over there. And Ohm's law still ends up being the same equation, where it's V equal to I times R. The R is still just 10 ohms, so the equations look the same. All right. So we just found that the equivalent resistance, I'll call it REQ, for a series circuit is equal to the addition of all of the resistors. If we have more resistors, we keep adding them. Okay. If we go back to that graph, we can see that the total voltage drop is equal to the voltage drop across each resistor. And that would equal the voltage here, which is equal to the voltage of the battery. Last thing would be looking at the current through the circuit whenever we have multiple resistors. Since there's only one path to flow, the current is constant throughout the circuit, which is why we pulled it out of our loop rule equation. Okay, so if we wanted to solve a problem using this information, to figure out the total current moving through the circuit, we would have to use these values right here. Okay? You'd have to know the total resistance and the total voltage supplied by the battery to figure out the rate of current flow. If we wanted to figure something out about the individual resistors, this current still applies in each of those individual situations. But you would have to kind of cluster the individual values together. So you can't use the voltage of the battery along with the resistance of just one of the resistors. We'll look at resistors in parallel in the next video.